Hey there, my name is Dawei Liu, and I'll be presenting on the second lab of Introductory Physics 2 at Georgia Tech titled Magnetic Field of a Bar Magnet. Shown here is a brief preview of the main results of the lab described in numerical form. The purpose of this experiment was to measure the distance dependence of a magnetic field due to a small neodymium magnet. We then simulate this magnetic field using Web VPython and then compare the measurements to the analytical results predicted by the Biot-Savart law. As for a preview, the magnitude of the strength of the magnetic field is shown to decrease as the distance increased, and the magnetic dipole moment was found to be about 3.1802 ampere meter squared. The observed off-axis magnetic field was approximately 3.11 times 10 to the negative fifth Teslas, and the predicted off-axis magnetic field, or simulated, was approximately 7.067 times 10 to the negative fifth. And shown here are the model's fundamental physical principles and relevant constants that were employed in this experiment. Firstly, the magnetic field of a dipole, which was off-axis, the Biot-Savart law, shown here for the dipole on and perpendicular axes, and then the magnetic dipole moment. The distance dependence of the magnetic field was also expressed in the following equation, K times R to the N, where K includes the magnetic moment and other parameters, while N was to be determined in this experiment through the procedures described. It was assumed that the magnetic field produced by a ring of current would be similar to that produced by a bar magnet. And using a magnetometer accompanying the Physics Toolbox Sensor Suite app that was downloaded from the App Store, I recorded the magnetic field measurements in 3 axes. The following statements were not observed during the experiment. As the magnetometer moved closer to the magnet, the measured X component of the magnetic field decreased, and the position of the magnetometer had no effect on the measured X component. Whereas the following statements that were observed were that the magnetometer, when it was far away from the magnet, measured a near zero magnetic field in the X direction, and as the magnetometer moved closer to the magnet, the measured X component increased. The system was shown to be the magnetometer and iPhone, while the surroundings that needed to be accounted for were the Earth and bar magnet. Shown at the bottom was a calculated adjustment from NOAA. Now, using a logarithmic plot of the triplicates of the distances in meters, produced the X component magnitude values at 20, 70, 120, 170, and 220 microteslas, and yielded by the following equation that was using a linear regression. By and Bz Earth were subtracted from the respective measured components to yield the corrected values, and equating the value of n to the slope of the graph and reversing the natural logarithm by raising e to the y-intercept allowed for the derivation of the magnetic moment, which was found to be approximately 3.1802 Newton meters per Tesla. Shown here are screenshots of the computational model that was employed in this experiment as well, in GlowScript, with code shown above and the corresponding physical analogy at the bottom. Shown again are the physical parameters that were used and assumed in this experiment, with a corresponding output showing the magnetic field and its direction. As for the main sources of error in this experiment, they resulted from the initial steps primarily of calibration and numerous discrepancies in external influences, distance, and readings. These included the presence of other electronics that could have altered the magnetometer readings, not lining up the phone with the magnetic north of before starting, improper placement and accidental movement of the phone, and incorrectly deducing where the location of the magnetometer would be in the iPhone 13. There were also random fluctuations in distance and potentially inaccuracies resulting from the phone magnetometer itself. Addressing the what-if of this lab's experiment, the magnetic field should not shift in the Z component, though it may shift in the X and Y components if the setup was not to compensate for magnetic north. And if two identical magnets were stuck together, then the combined magnetic field should increase in strength by a scalar factor, or approximately double, as one magnet may superpose with the other. Thus, the distances may decrease. as they could be treated as a single larger magnet. In conclusion, the magnetic field of a bar magnet may be modeled both computationally and analytically using an equation. However, this may be due to a questionable degree of accuracy due to confounding factors and other unaccounted sources that were not compensated for. Thank you.